Hello, this is our third class on X-ray. Here we learn how to solve the X-ray related numericals. We will basically follow the numericals from the book, the exercise. So let's solve them out. Okay, first of all, the first numerical. So before solving the numericals, we must need to remember what are the formulae. The actually important formulae are three. One is the formulae for maximum frequency, the nu max. How to calculate the maximum frequency of X-ray that will come out. The maximum frequency of X-rays formula is this, equals to EV by H, where E is electronic charge, V is the potential difference applied, means how much voltage you are giving, and H is Planck's constant. I am not mentioning that any further. That 6.6 value is known to all of you. So this is the formula for maximum frequency of X-ray that will be emitted for a particular potential difference. This is the first important formula you require. The next formula is for minimum wavelength of the X-ray. These two formula will take out the most number of numericals. Minimum wavelength. Now the question appears how to calculate that. Yep, it's very easy. Last day we have derived it. You can watch the previous video for it. Lambda minimum equals to Hc by Ev. Similar quantities. H Planck's constant, E is electronic charge, V is the potential difference, and C is the velocity of light. Clear? And the third formula will be the Moseley's law. It is sometimes required in very few numericals. They are asked often, and that formula is that this is called Moseley's law. It is called root nu, where nu is the frequency of the element, the k alpha line frequency. H square root is equals to k times z minus b, where nu is here the k alpha line frequency and z is atomic number. The other k and b are two constant. Those will be usually supplied. Okay, so these are the entities. These three formulas you must need to remember for these cases. Clear? And if sometimes you forget some values while calculating the kinetic energy of the electrons or such kind of scenarios, you have to remember some values. I'm writing all it for you. It's like E, that is the charge of an electron, is 1.6 into 10 to the power minus 19 coulomb. The mass of an electron is 9.11 into 10 to the power minus 31 kg. And all kinds of wavelengths are expressed in Armstrong, and 1 Armstrong is equals to 10 to the power minus 10 meter. One more, Planck's constant. That value is often given in the problems. Still, usually 6.6 into 10 to the power minus 34. The unit is joule second. And velocity of light is known to all of you. So these values are often required while solving the numericals. Please note them down if required. Now we will start the first numerical. The first numerical suggests if the potential difference applied in a Coolidge tube is 28.8 kV, means kilovolt, find out the maximum kinetic energy of the electron and the velocity of the electron. So my potential difference is 28.8 kilovolt. That is 28.8 into 10 to the power 3 volt. Clear? That's the value of C. Now what is the kinetic energy of the electron? Kinetic energy of the electron, which is passed through a potential difference of V, is what is? I hope all of you remember. This is EV, means the charge of an electron multiplied by the voltage applied. So charge all of us know, and this is multiplied with the potential difference. Clear? Let's see the answer. What does it give? We have 1.6 10 to the power minus 19 28.8 into 10 to the power 3. The answer is 4.608 into 10 to the power minus 15. And of course the unit of kinetic energy is always joule. So this is the first problem. The second part is calculated the velocity. Okay, of course I know the kinetic energy, and the formula after you know the kinetic energy is half mv square, and half mv square, which is kinetic energy, that value I've got 4.608 into 10 to the power minus 15. So the velocity, this v can be easily calculated because mass is known to us. So you can see how can we solve it, that v square equals to 2 into 4.608 into 10 to the power minus 15. Here is a minus symbol, don't forget that, divided by this m coming to the denominator. M is the mass of the electron, because in this question we are actually accelerating the electron. So mass of that electron must be calculated. The mass we know is 9.11 into 10 to the power minus 31 kg. Okay, so if I do that, what shall I get? 4.608 multiplied by 2 . So our answer comes out to be 1.01 into 10 to the power 16, and that is the answer of v square. Hence v will be square root of the v square, and the square root of the answer is how much? The square root of the answer is 1.01 into 10 to the power 8 meter per second. So please solve it out. This is the second part of the numerical we have been calculating. So that's numerical number of 1 is done. Next we are going to the numerical number 4, that was asked in ISC 2008. Okay, numerical number 4 is depending on the second formula, the minimum wavelength to be generated. See, it is said calculate the minimum wavelength of X-rays emitted by an X-ray tube operating at a tube potential P is 40 kV. 40 kV means 40 into 10 to the power 3 kilovolt to volt, 10 to the power 3 conversion volt. How will this wavelength change? In if target mode is another material, we will also find this portion, but let's find out the minimum wavelength. The minimum wavelength, lambda mean, the formula we have written before, hc by ev. So 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8 divided by 1.6 into 10 to the power minus 19 coulomb into potential difference is 40 into 10 to the power 3. What that value is given, we have to calculate this now. So if I just put into the formula, we will find out something which is 0.31 into 10 to the power minus 10 meters. And this 10 to the power minus 10 meter can be written in terms of Armstrong, because 1 Armstrong equals to 10 to the power minus 10 meter. So the answer can be written in 0.31 Armstrong. Clear? Now, the next part of the question, it is asked, how will this wavelength, means this minimum wavelength value, will change if target made on another material? Means in this question, if I just change the material but bring everything same, you can see the lambda minimum formula here. The minimum wavelength depends on h, which is a constant, c, which is also another constant, e, the electronic charge, another constant, just the factor is v. V, the driving potential. Clear? Now you can see the driving potential, if I give the same amount of potential on any target, it will give the same wavelength. So the answer will be, it will not change. There will be no change if I just change the material which I am using in the Coolidge tube target. Yeah, so that's a quite easy numerical we have done. That is question number 4. It came in ISA 2008. Next question we will solve is, let's solve out question number 6. 6 is also minimum wavelength. Similar numericals are asked. Still solve it because it came in ISC. Number 6 tells us that find the minimum wavelength of the emitted X-rays when an X-ray tube is operating at 50 kilovolt. The operating voltage is 50 kV. That is 50 into 10 to the power 3 volt. Okay, so you can see here that's the driving potential. Now minimum wavelength, that's easy formula, HC by EV. So 6.63 into 10 to the power minus 34 into 3 into 10 to the power 8, that's the velocity of light, C, by E. Sorry, the writing is not okay here. Let's read properly. 1.6 into 10 to the power minus 19 into 50 into 10 to the power 3. Clear? Just calculate this, put the values in your calculator. I'm also calculating in mine. The value is 2.48. The value I got is 2.48 into 10 to the power minus 11 meter. That can be written as 0.248 into 10 to the power minus 10 meters. Now 10 to the power minus 10 meters can be easily expressed as 1 Armstrong. So lambda minimum, which value is 0.248 into 10 to the power minus 10 meters, can easily be expressed as 0.248 Armstrong. That is also the case of another minimum wavelength calculation. So you can see most of this maximum frequency and minimum wavelength numericals are coming in ICSC. So give proper importance to them. That's what is required. Clear? So these 2 numericals, rest 5, 6 numericals you can do. For the last numerical, question number 9, that numerical is not required for your class. That's mostly not preferred by ISC. If you have an internship, you can go and solve those things. So thank you. Your work for this week is to solve all the numericals of X-ray. If there are any doubt, any further doubt, comment me, write me. I will solve your all the doubts. So thank you, class. Have a nice day.